Next, we will discuss how to use the inverse substitution technique to integrate functions that have a certain pattern. The idea is very simple. When you see a radical of some number a squared minus some number b squared multiplied by x squared, consider replacing x with a over b times the sine of theta. So theta being a new variable means we have to find dx in terms of d theta and replace every appearance of x with theta. The reason why such substitution may work is that when x is equal to a over b sine theta, the differential of x is simply a over b times the cosine of theta, d theta. And to see what happens to the original radical expression, we replace x with a over b sine theta, distribute the square over the product, simplify, and factor the common factor a squared. Then, after using the Pythagorean identity and the properties of the square root, we finally rewrite the original expression as the product of the absolute values of a and the cosine of theta. Assuming that a is positive and theta is between negative and positive pi over 2, allows us to get rid of the absolute values. As a result, we now have very nice expressions in terms of theta for both the differential of x and the original radical. This substitution leads to a new integral, which is now of some combination of trigonometric functions of theta. Let's do an example. We first recognize the distinct pattern and set up the substitution by setting the variable x equal to 4/3 of sine of theta, and finding the differential of x and the radical expression in terms of theta. Next, we plug everything into the original integral and simplify so that we have nothing but a trigonometric function of theta left in the integrand. We continue with the process by finding and simplifying the antiderivative of the trigonometric function. And to finish the process, we need to replace theta with the original variable. To find theta, we consider the substitution and isolate theta by applying the arcsine function to both sides of the equation. To find the cotangent of theta, we construct the reference triangle for angle theta, find the missing adjacent side using the Pythagorean theorem, and use the definition of cotangent to express it in terms of x. We finish the process by replacing theta and the cotangent of theta with the expressions in terms of x and simplifying the result. Let's do another example. We first recognize the distinct pattern and set up the substitution by setting the variable x equal to 1/5 of sine of theta, and finding the differential of x and the radical expression in terms of theta. Next, we plug everything into the original integral and simplify so that we have nothing but a trigonometric function of theta left in the integrand. We continue the process by finding and simplifying the antiderivative of the trigonometric function. To finish the process, we need to replace theta with the original variable. To find theta, we consider the substitution and isolate theta by applying the arcsine function to both sides of the equation. To find the cosine of theta, we construct the reference triangle for angle theta, find the missing adjacent side using the Pythagorean theorem, and use the definition of the cosine to express it in terms of x. We finish the process by replacing theta and cosine of theta with the expressions in terms of x and simplifying the result. Let's do an example of a definite integral. One approach is to go through the process of finding the indefinite integral and then use the fundamental theorem of calculus at the end. However, there is an easier approach. Alternatively, we can change the limits of integration right after introducing a new variable. Since x is equal to 1/5 of the sine of theta, then theta is equal to arcsine of 5x. Hence, when x is 0, theta is also 0, and when x is 1/10, theta is equal to pi over 6. Next, we set the new limits of integration, plug everything into the original integral, and simplify, so that we have nothing but a trigonometric function of theta left in the integrand. We continue with the process by finding and simplifying the antiderivative of the trigonometric function. And to finish the process, we use the fundamental theorem of calculus by plugging in the lower and upper limits of the integral. And we get the final answer. Let's do another example. We first recognize the distinct pattern and set up the substitution by setting the variable x equal to 4/3 of sine of theta, and finding the differential of x and the radical expression in terms of theta. We change the limits of integration right after introducing a new variable. Since x is equal to 4/3 of sine theta, then theta is equal to arcsine of 3x over 4. Hence, when x is 2/3, theta is pi over 6, and when x is 4/3, theta is equal to pi over 2. Next, we set the new limits of integration, plug everything into the original integral, and simplify, so that we have nothing but a trigonometric function of theta left in the integrand. We continue with the process by finding and simplifying the antiderivative of the trigonometric function. To finish the process, we use the fundamental theorem of calculus by plugging in the lower and upper limits of the integral. And after simplifying, we get the answer. We discussed and practiced an integration technique called the inverse trigonometric substitution, applied to both indefinite and definite integrals.